100 years after we discovered the quantum realm, the people who built the most predictive theory in the history of science still cannot agree on what it is describing. 45% say the line between the quantum world and the world you live in is real. 45% say there is no line at all. Underneath that disagreement, every atom in your body is running rules that, taken seriously, deny that you have a definite location, a definite history, or a single shared world to live in. Tonight, we are going to walk down into the realm together and look at what is actually there. So get comfortable, pull the blanket up, and settle in. The realm has been hiding something in plain sight. We are about to notice it. There is a fact about the universe that scientists discovered a little over 100 years ago, and we have, collectively, decided not to think about it too hard. The fact is this: the world you see when you look around the room, the wood of the table, the warm light from the lamp, your own hands resting in your lap, is not the world that exists at the smallest scales. At the smallest scales, the universe runs on rules that have almost nothing in common with the rules you live by. And the strangest part of the whole story is not that those rules exist. The strangest part is that, if you follow the math carefully, those rules never actually switch off. They run all the way up. They are running, right now, inside your body, inside the floor, inside the air between you and the screen. We just lose track of them very quickly because the world is loud. Tonight, I want to take you for a walk down into that smaller world. Not in a hurry. Not with alarm in my voice. Just slowly, carefully, the way you might take a stranger through your house and point out the things they would not have noticed on their own. The quantum realm has the reputation of being weird, and it is. But the word weird is too small. What we are going to look at, together, is something closer to a slow revelation. The kind of revelation that does not arrive all at once, but accumulates, one careful observation at a time, until the world you started in does not quite look like the world you end in. In July of 2025, the journal Nature published the results of a survey conducted to mark 100 years since the formal birth of quantum mechanics. The survey asked working physicists what they actually believed about the theory they used every day. The answers, when collected, told a story most outsiders would find genuinely unsettling. About 15% of physicists said they preferred the many worlds interpretation, in which every possible outcome of every measurement actually happens. The rest was split across half a dozen rival pictures. Some said the wave function collapses when you measure it. Some said it never collapses, and the world only looks that way. Some said the whole formalism is just a tool for updating beliefs. Some said the question of what is going on between measurements does not have an answer. Most strikingly, the survey asked whether there is a real boundary between the quantum world and the classical one, between the rules that govern atoms and the rules that govern the chair you are sitting in. 45% of the respondents said yes, there is a real boundary. 45% said no, there is no boundary. After 100 years of building the most successful theory in the history of science, the people who use it every day cannot agree on whether the line between down there and up here is real. That is the situation we live in. And the rest of physics carries on as if this is fine. Now, when I say the most successful theory in the history of science, I am not exaggerating. Quantum field theory, the modern descendant of the rules we are about to walk through, predicts the magnetic behavior of a single electron to roughly 12 decimal places, and the experimental measurement agrees with the prediction to that same precision. Nothing else in science is that good. We have a description of nature so accurate that we cannot push the comparison any further without building better instruments. And we still do not know what the description is describing. So how did we get here? Let me take you back to a small dark room in Manchester, England, in the early 1900s. A physicist named Geoffrey Taylor sets up an experiment that an Englishman named Thomas Young had first done with sunlight 100 years before him. Taylor, however, dims the light so far down that, on average, only a single particle of light is in his apparatus at any one time. He sets up 2 narrow slits in a screen and a piece of photographic film behind them. Then he leaves the experiment to run for months, letting individual particles trickle through one at a time. When he finally develops the film, he finds an interference pattern, stripes. Bright bands and dark bands, exactly the pattern you would get if light were a wave passing through both slits and interfering with itself on the other side. But each particle had arrived alone. There was nothing for it to interfere with, except, somehow, itself. One photon, with nothing else in the apparatus, behaved as if it had taken both routes through both slits at the same time, and then the 2 ghost copies of itself had recombined to make a pattern on the far side. 50 years later, a German physicist named Klaus Jonsson did the same experiment with electrons. Same result. The electron, alone, interferes with itself. In 2019, a group at the University of Vienna did the experiment with molecules made of about 2,000 atoms each. Things larger than the smallest viruses. Things you could, in principle, photograph. And they too made interference patterns. They too behaved, in flight, as if each one were taking every possible path between source and detector, simultaneously, and only deciding which one it had taken at the moment it landed. This is the quiet discovery I want you to sit with. The rules do not stop. They do not have a height limit. They do not say, I only work for tiny things. They have been pushed up, slowly, into the territory of objects we can see in microscopes. We have not found the place where they break. We have only found the places where the noise of the world has grown loud enough to wash them out. You and I are made of atoms that obey those rules. The chair beneath you is made of atoms that obey those rules. The walls and the ceiling and the screen in front of you. The only reason any of it looks solid and definite and located in one place at a time is that there are so many atoms jostling so loudly that the underlying pattern gets averaged into something stable enough to share with one another. Underneath, the substrate has never agreed with our intuitions. It has only let them stand as a kind of useful approximation for as long as we did not look too closely. The point of this video is to look closely. We are going to walk down through the layers, one at a time, and watch our intuitions break. We will start with what the quantum realm even is. Then we will visit its main strange features: superposition, entanglement, measurement, the weight of empty space, the meaning of the wave function. By the end, we will have arrived at a question, and the question is what the title of this video is really asking. What is hiding down there? What does it want with us? And what does it mean for the world we thought we lived in? I will tell you now, gently, what I think the answer is. The thing hiding inside the quantum realm is not a creature. It is not a hidden room. It is the suspicion that the world you live in is not the world that exists. The world you live in is the projection. The realm is the source. And the door, once opened, cannot be closed. Now, before we go any further, I want to address something that often comes up when people first encounter the strangeness of quantum mechanics. There is a temptation to dismiss the whole thing as mathematical games, to assume that the weirdness lives inside chalkboards and equations, and that the world out there, the world of furniture and weather and skin and sky, is fundamentally as it appears. The temptation is understandable. Our minds were not built to confront the kind of news the realm has been quietly delivering for the past century. So we file it under interesting curiosities, and we move on with our lives. And the framework, predictively perfect as it is, makes that filing possible. Quantum mechanics tells you what your detector will read. It does not insist you understand why. You can use the theory all day long, build careers around it, design technologies with it, and never once look directly at what it is saying about the substance of reality. Most physicists, in fact, do exactly that. They calculate, they publish, they do not interpret. The strangeness is left on a shelf in another room, and the door is closed. But the door does not stay closed forever. Every so often, somebody opens it. Every so often, a new experiment forces a conversation that everyone had been politely avoiding. The aspect experiments in 1982 opened the door on entanglement. The delayed choice experiments of the 90s opened it on the role of the observer. The decoherence work of Zurek and others in the same era opened it on the boundary between quantum and classical. In each case, the news arrived. The textbooks were quietly updated, and the door, by general agreement, was closed again. The work of taking the news seriously was deferred. We are now 100 years into deferring it, and the news has been accumulating in the deferred pile, and the pile, at this point, has become large enough that you cannot walk around it. Tonight, we are going to look at it, carefully, in order, without alarm, because the news, once you sit with it, turns out to be more interesting than it is terrifying. So, settle in. The first thing we need to do is figure out what we are actually talking about when we say the realm. It turns out the answer is closer to home than anyone expected, is less than break time equals 1s, is greater than. When people hear the words the quantum realm, they tend to picture somewhere else, a hidden country, far away, with its own rules. The word realm carries a kind of fantasy weight, as if we were describing a kingdom you could visit if you were brave enough. That image is wrong, and it is wrong in a way that matters. There is no quantum country. There is no door. The realm is not a place. The realm is a regime. Let me show you what I mean by walking us down through scale, slowly, until classical intuition begins to fail. Start with your own hand. A single strand of your hair is about 10 micrometers across. That is 10 millionths of a meter. If you laid 100 of them side by side, they would just barely fill the width of a millimeter. Each strand is still, comfortably, a thing in the world. It has a position, it has a length. You can see it with the naked eye and feel it between your fingers. Nothing weird yet. Drop down by a factor of 10 and you arrive at the cells in your skin. Drop down by another factor of 10 and you arrive at bacteria, the small living things growing on the surface of your hand at this very moment, still small enough to behave like everyday objects. They eat, they move, they divide. You can see them with a decent optical microscope. The rules of your world still apply. Drop down by another factor of 10 and you arrive at viruses, about 100 nanometers across, things made of a protein shell and a small ribbon of genetic instructions. They begin to act stranger, but mostly in biological ways, not in physical ones. The rules of the everyday world still bend to accommodate them. Drop again by a factor of 10, and you arrive at the size of a typical protein, 10 nanometers. Something is starting to happen here. The molecules at this scale, when you watch them carefully, do not move smoothly. They twitch and snap and refold with a randomness that you start to suspect is not just thermal noise. Some of their behavior begins to require the new rules to explain. Drop again by a factor of 10 and you arrive at the size of a single atom. About 1/10 of 1 nanometer. This is the edge. This is where classical physics goes off the cliff. Not because we have failed to describe the atom with classical rules, we have certainly tried, but because the atom, when you push on it carefully, refuses to obey them. It refuses, in a perfectly consistent and well-documented way, that has been the subject of a century of careful study, and the refusal turns out to be the most important thing about it. Let me draw the atom for you, by ratio, so you can feel what is actually in there. Imagine you scaled up a single hydrogen atom until it was the size of a football stadium. The nucleus, the small, heavy part at the center, would be a single marble sitting at the 50-yard line. The rest of the stadium, from the marble all the way out to the upper seats, would be the space the electron occupies. And it would contain nothing else. That is the structure of matter. An atom is roughly 99.9999999999996% empty space. You can read out those nines until you get tired. The percentage barely moves. The solid feeling of the floor beneath you, the weight of the cup in your hand, the resistance of the wall when you knock on it, all of it is generated by something that, by volume, is overwhelmingly nothing. The atoms in your fingertip do not touch the atoms in the cup. They never touch. They simply repel one another through the electromagnetic field, and what you feel as touch is the field's resistance. But here is the part that breaks the picture. The marble in the middle, that is real. It has a location, more or less. The electron, the part filling most of the stadium, does not. I do not mean it is moving so fast you cannot keep track of it. I do not mean we have failed to measure it well enough. I mean it does not have a position the way the marble does. The electron does not sit somewhere and orbit. The electron is described by a thing called the wave function, which assigns a kind of probability to every possible location the electron might be found in. When you measure, you find the electron at one of those locations. When you stop measuring, the electron, in some sense that nobody has ever fully agreed on, goes back to not being anywhere in particular. The cloud is not a haze of motion. The cloud is the thing the electron is. And now you can begin to feel why the rules of your world fail down here. Your world is built on the assumption that things have positions and properties, even when you are not looking at them. That assumption, at this scale, stops being justified. We cannot prove the electron has a position when we are not measuring it. We cannot prove it does not. The theory works whether you say one or the other, as long as you do not insist that nature has to make a choice. This is what Werner Heisenberg discovered in 1927 when he wrote down what we now call the uncertainty principle. The popular version of the principle says that you cannot know both the position and the momentum of a particle at the same time. That version is correct as far as it goes, but it suggests the limitation is about us, about our instruments, about our skill. The real principle is more disturbing. It says that the particle does not have a precise position and a precise momentum simultaneously for there to be known. The values are not waiting for us to discover them. They do not exist together. Position and momentum for a quantum object are not properties of the object in the way that color and weight are properties of an apple. Energy, in this regime, also stops behaving the way you expect. In your world, energy flows continuously. You can have any amount you like. Down here, energy comes in steps, discrete steps. Max Planck noticed this in 1900, when he was trying to explain the spectrum of hot objects and could only get the math to work if he assumed that energy came in small, indivisible packets, which he called quanta. The word gave the field its name. Albert Einstein took the idea further in 1905, when he showed that light itself was made of those packets, photons, and that the photoelectric effect, in which light knocks electrons out of metals, only made sense if you treated light as quantized. The world, in other words, is digital at its base. Continuous-looking quantities, when examined carefully, are made of discrete jumps, too small for us to see. Everything you experience as smooth is mosaic underneath. You can keep going down. Below the atom, you find the nucleus, made of protons and neutrons, each one about a femtometer across a millionth of a billionth of a meter. Below the proton, you find quarks, which appear to be point-like as far as anyone has been able to measure, smaller than 10 to the minus 18th meters. Below that, theory predicts a place called the Planck length, at one point 6 times 10 to the minus 35th meters, where we suspect that the idea of length itself breaks down. The ratio between a proton and the Planck length is greater than the ratio between a proton and the entire observable universe. There is more down left in the realm than there is up in the sky. We have not been to the Planck length. We do not have instruments that can resolve it. We do not know if our rules still work at the bottom because we have not been able to look. Now, here is the pivot I want you to take with you into the rest of this conversation. The realm is not somewhere else. The realm is what you are made of. Every atom in your bones, your blood, your eyes, your nervous system is running these rules right now. The only reason you are not aware of it is that there are so many of them, behaving so chaotically together, that the underlying pattern smears into the simple, stable picture you call your body. Underneath, the rules have never stopped. We just learned not to look. Most of what feels solid to you is empty space. And the part that is not empty is doing things that, if you watch them up close, would make the world you live in look like a very polite lie. That is where we are going next. We are going to start with the strangest of the rules, the one that almost everyone has heard of, and almost no one really believes. A thing can be two things at once, is less than break time equals 1s, is greater than... Let me start with the wave function. I have been mentioning it casually for 2 parts now, but it is time to look at it directly, because almost everything strange about the quantum realm flows out of this single mathematical object. The wave function is a thing physicists write down to describe a quantum system. It is, in the simplest language I can give you, a complete description of every possible thing the system could be doing, all at once, with each possibility weighted by a number that tells you how likely that possibility is to show up if you measure. Not a description of where the electron actually is, a description of every place it might be, simultaneously, with the weights attached. Now, you might be tempted to read that and think, this is just bookkeeping. The electron is somewhere. The wave function is the list of guesses we have not narrowed down yet. As soon as we measure, we narrow it down, and there it is. That sounds reasonable. The math will not let you believe it. Here is why. The wave function is not a list of mutually exclusive guesses. It is a sum of complex numbers, numbers with a magnitude and a kind of rotation, called a phase. When 2 parts of the wave function meet, when, for example, 2 different paths the electron could have taken come back together at a detector, the complex numbers add. Sometimes they add constructively, making the probability of detection bigger. Sometimes they add destructively, making the probability smaller. Sometimes they cancel completely, and the electron is never detected at that spot at all, no matter how many tries you give it. That cancellation is the thing your "it was always somewhere" interpretation cannot explain. If the electron had taken one path or the other, you would never see cancellation. You would see a sum of probabilities. What we see, in experiment after experiment, is a sum of complex amplitudes, with phases that interfere. The other possibilities are not just guesses we have not eliminated. The other possibilities are leaving fingerprints on the world. They are real enough to add and subtract from each other. Bring back the double-slit experiment. A single electron is fired at a barrier with 2 narrow openings, with a detector screen on the far side. Over thousands of repetitions, you build up an interference pattern. Bright stripes where the 2 paths added constructively. Dark stripes where they cancelled completely. Now, here is where it gets stranger. Block one of the slits. The interference disappears. The pattern collapses into a simple smear, as if the electron had just gone through the open hole and landed somewhere on the far side. Open both slits again. The interference comes back. The electron is reacting to what is available to it, not to what it actually did, to what it could have done. If both slits are open, both paths contribute. If only one is open, only one does. The electron, in flight, somehow knows about the existence of both slits. even though, as a single particle, you would expect it to only know about whichever one it actually went through. There is a temptation to say, maybe the electron is actually a wave during the trip and a particle when it lands. That is half of the right idea. The other half is that wave and particle are not two things the electron can be. They are two stories we tell about a single underlying object, the wave function that has, in itself, properties of both. The realm does not contain waves and particles as separate kinds of stuff. It contains wave functions, which become wave-like or particle-like, depending on what we measure. This is what physicists mean by superposition. The system is not in any one of its possible states. It is in a sum of them, with the different parts able to interfere with each other. A thing can be two things at once, because there is, at the substrate level, no rule that says a thing has to be one thing. The rule that says a thing has to be one thing is something we imposed when we built our intuitions out of human-scale experience. The most famous illustration of superposition is, of course, Schrödinger's cat. Erwin Schrödinger wrote it down in 1935, in a paper meant to be sarcastic. He was trying to point out how absurd the implications of his own theory had become. Imagine, he said, a cat in a sealed box, along with a vial of poison that would be released if a single radioactive atom decayed. The atom, by quantum rules, is in a superposition of decayed and not decayed. By extension, the poison vial is in a superposition of broken and unbroken. By extension, the cat is in a superposition of dead and alive. Schrödinger meant this to be ridiculous. He meant his colleagues to laugh and admit they had pushed the math past its sensible limits. The colleagues laughed. Then they kept using the math, because the math kept being correct. In the years since, physicists have built actual versions of Schrödinger's cat in their laboratories. Not literal cats, but objects much larger than atoms held in superposition between two states. Superconducting qubits, small loops of metal cooled to near absolute zero, have been placed in a superposition of two different current flow patterns at the same time. Each of those patterns involves billions of electrons flowing in concert. The whole loop, billions of electrons strong, sits in two opposite states until you measure. Mechanical resonators, small drums made of crystals, have been put into superposition between vibrating and not vibrating. Strange atoms, large enough to see with the naked eye if they were prepared in the right conditions, have been held in superposition for hundreds of microseconds. The principle does not stop at the atom. We keep pushing it up. The experimental record now contains macroscopic superpositions that, by Schrödinger's 1935 standards, should have been impossible. And here is the part that should genuinely disturb you if you sit with it. The wave function describing two entangled particles does not live in three-dimensional space. It lives in 6. For 3 particles, 9. For 100 particles, 300. For all the particles in a coffee cup, more dimensions than there are atoms in the visible universe. I am not speaking poetically. I am telling you what the math does. The wave function, as a mathematical object, requires a space whose number of dimensions grows with the number of particles you are describing. That space is called configuration space, and it is the natural home of quantum mechanics, and it does not fit inside our three-dimensional world. 2 options follow from this. Either the wave function is not really real, and we are using a fictional mathematical object that, somehow, just happens to predict the future to 12 decimal places, or the wave function is real, and the world you live in is a 3-dimensional shadow being cast by an object that lives in a higher dimensional space we cannot see. Pick one. Each is upsetting in its own way. There is a separate, related strangeness that comes out of superposition, and I want to spend a moment on it because most introductions skip over the implications. When a quantum system is in superposition, the system does not just contain multiple possibilities. It contains them with specific phase relationships between them, and those phases matter. The phase is like the angle of a small clock hand attached to each possibility. When two possibilities meet, the clock hands have to be added together. If they point in the same direction, you get reinforcement. If they point in opposite directions, you get cancellation. The world we observe is the result of adding all the clock hands of all the possibilities with their proper rotations and reading off the answer. This is what makes quantum mechanics fundamentally different from classical probability. In classical probability, if you flip a coin and forget which side came up, you just have a mixture heads with 50% likelihood, tails with 50%. The two possibilities never interfere with each other. They just sit there as alternatives. In quantum mechanics, the two possibilities have phases, and those phases mean the alternatives can add, subtract, or cancel one another. This is not a quirk. This is what makes the realm not just unknown, but actively strange. Classical probability says, we don't know which one happened. Quantum mechanics says, all of them are happening with specific phases, and the phases interfere. You may be wondering then, why the world looks so reliably solid and singular if all of this is going on underneath. The short answer is that the quantum strangeness gets erased by the noise of the environment in a process called decoherence. The full answer is what we are going to spend the next several parts unpacking. The very short version is this. As soon as a quantum system interacts with enough other particles, air molecules, photons of light, the warm jiggling of the surrounding matter, the precise phase relationships between its possibilities get scrambled. The clock hands lose track of each other. The interference disappears, not because the possibilities have stopped existing, but because they have become so entangled with the environment that you cannot, in practice, recover the patterns they would have made. Decoherence is what makes superposition look like ordinary uncertainty at human scales. It does not solve the measurement problem, we will see why later, but it explains why we never see Schrödinger's cat in a state of both at once when we open the box. By the time the box is open, the cat's quantum information has leaked into so many other particles that the original superposition is, for all practical purposes, gone. But first, we have to look at the next rule. Because superposition, on its own, is only weird. What happens when you take superposition and apply it to two particles at the same time is something much harder to live with. Two particles can become a single fact, distributed across any distance, with no story you can tell about how that fact was carried between them. Stay with me. We are about to walk into the longest shadow physics has ever cast. Is less than break time equals 1s? Is greater than? In 1935, Albert Einstein, with his colleagues Boris Podolsky and Nathan Rosen, published a paper meant to expose what they believed was a fatal flaw in quantum mechanics. The paper was a thought experiment. It went like this. Take two particles. Prepare them together in a single quantum state so that their properties are correlated. Then separate them. Send one to a laboratory in Princeton and one to a laboratory in California. Measure one of them. The math of quantum mechanics, applied to this setup, said that as soon as you measured the property of the Princeton particle, the property of the California particle was fixed. Not in a we now know what it is sense, but in an it now is what it is sense. The act of measurement at one end of the country, the math said, determined the state of the particle at the other end, instantaneously, without anything travelling between them. Einstein, who had built his reputation on the principle that nothing can travel faster than light, found this impossible to accept. He called it spooky action at a distance. He wrote it down precisely so that any sensible physicist would see the problem. He thought it would end the debate. It did not. Quantum mechanics kept making predictions. The predictions kept being correct. Einstein went to his grave, still convinced that there had to be hidden variables, properties the particles carried with them, secretly, that would explain the correlations without requiring spooky action. He just did not know what the variables were. For 30 years, the question sat unresolved. Then, in 1964, an Irish physicist named John Bell, working at CERN, proved a theorem that, in retrospect, settled the matter forever. Bell showed that any theory in which the particles had definite properties before being measured, and in which no signal travelled faster than light between them, had to satisfy a particular mathematical inequality. Quantum mechanics predicted that the inequality would be violated. The two theories made different predictions. The experiment could decide. Alain Aspect, a young French physicist, did the experiment in 1982. He prepared pairs of entangled photons, sent them to detectors at opposite ends of his laboratory, and measured the correlations. The inequality was violated. Quantum mechanics was right. Einstein, on this point, was wrong. There were no local hidden variables. The world really did contain correlations between distant particles that no story about local objects could explain. In the decades since, the experiment has been refined and repeated under conditions designed to close every conceivable loophole. The 2022 Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger for that work. The Nobel Committee, an institution not given to drama, explicitly recognized the result as settling the question. Local realism, as a description of nature, is dead. We have to give up either the idea that particles have properties before they are measured, or the idea that no influence can travel faster than light, or both. Most physicists give up locality. They accept that quantum correlations are non-local in some sense, without admitting that this lets you send signals faster than light. And it does not. The correlations are real, but they cannot be used to transmit information. You only see the pattern after both sides compare notes through a classical channel which travels at light speed. A few physicists give up realism, taking the position that particles simply do not have properties between measurements. A handful superdeterminists, like Gerard Hooft and Sabine Hossenfelder, give up the freedom to choose what to measure, arguing that the universe was set up at the Big Bang in a way that makes every experimenter's choice already correlated with the result they will find. Each of these options is its own special kind of upsetting. Now, what does entanglement actually do in practice? Let me give you a feel for it. When you entangle two photons, for example, in such a way that their polarizations are perfectly correlated, then if you measure the first photon's polarization along some axis and find it vertical, you can predict with certainty that the second photon, measured along the same axis, will also be vertical. If you measure the first one horizontally and find it horizontal, the second one will be horizontal too. That part, by itself, is not surprising. You could explain it with any number of classical correlations. They were prepared the same way. Of course they match. The surprise comes when you measure them along different axes. Quantum mechanics predicts a specific statistical pattern of agreement and disagreement that depends on the angle between the two axes. The pattern is mathematically incompatible with any classical correlation, no matter how clever you are about choosing hidden variables. Bell's inequality is precisely the bound that classical correlations cannot exceed. Quantum mechanics breaks that bound. Experiments confirm the violation every time. In 2017, a Chinese satellite called Mitchis sent entangled photons to ground stations more than 1,200 kilometers apart. The correlations held. The distance did nothing. The entangled pair was still, in some sense, a single object distributed across the surface of the Earth. In late 2025, scientists at Gila in Boulder, Colorado, succeeded for the first time in entangling two atoms that were also in motion. Atoms have mass. Mass interacts with gravity. The experiment is small, but it is a first step toward the long-standing question of whether quantum non-locality survives in the regime, where Einstein's other theory, general relativity, also has something to say. Nobody knows yet whether gravity can carry entanglement, or whether the substrate has rules at that scale we have not yet uncovered. The experiment is a door to the rooms we have not entered. In April 2026, a research group announced a new technique for measuring quantum entanglement inside solid materials. Not in carefully prepared isolated atoms in a trap, with everything else turned off, inside actual chunks of solid stuff, sitting at room temperature, with all the noise of the everyday world present. The result is that everyday solid matter is, at the quantum level, knotted together. Entanglement is not exotic. Entanglement is structural. The everyday objects around you are full of it, constantly, although you cannot see it from where you are. Also, in 2026, researchers demonstrated quantum teleportation across 270 meters of fiber optic cable running through the streets of a city using photons generated by quantum dots. Quantum teleportation, you should understand, is not Star Trek. It does not transport matter. It transfers the quantum state of one particle onto another at a remote location, destroying the original in the process. The information that crosses the gap is purely quantum. The matter stays where it was. But the state, the pattern, the fingerprint of identity that travels through entanglement, and a small amount of classical information sent alongside. What was once a thought experiment is now urban infrastructure. Now bring this back home. The picture that comes out the other side of these experiments is the following. Particles, when they interact, become entangled. Once entangled, their states are part of a single shared description. That description does not live in either particle separately. It lives in the relationship between them. When they part ways, the relationship goes with them, distributed across whatever distance you push them to. The correlations that follow from it are not carried by anything. They are simply there as a property of the pair, intact across any separation. The realm is woven together. This is not a special exception. This is the natural state of matter. Things in contact become entangled. The entanglement spreads. We do not notice in our daily life because the noise of the environment, what physicists call decoherence, rapidly washes the visible signatures out for human-scale systems. But the underlying weave is always there. Every molecule of air in this room is entangled with every other one that it has bumped against. Every cell in your body, every atom in the chair. The world we see, with its tidy separation of objects, is the surface of an ocean. Underneath, everything is one piece of cloth. This is the central thread we keep returning to. The realm runs on correlations our intuitions cannot encode. The stable, located, separable world of our experience is what surfaces above that weave, not what underlies it. The substrate refuses to be made of parts that have their own private lives. I want to slow down and make sure one more piece of entanglement lands properly, because it is the piece most often misunderstood in popular accounts. People sometimes say that entanglement lets you send messages faster than light. It does not. The correlations between entangled particles, although they are perfectly synchronized across any distance, cannot be used to transmit any information from one side to the other. Here is why. When you measure your particle, you get a random outcome. That outcome is correlated with what someone at the other end will see if they measure their particle. But neither of you can choose what your outcome will be. You can only see what the universe gives you. You cannot encode a message in the outcomes because you do not control them. The pattern only becomes visible after both observers have compared their results, and the comparison has to be sent through a classical channel which is bound by the speed of light. The entanglement is real. The correlations are real. The non-local connection is real. But the no-signaling theorem, proved rigorously in the 1970s, guarantees that no usable information crosses the gap. This is one of the most elegant facts in physics, and also one of the most frustrating. The universe contains demonstrably correlations that defy any local explanation. And yet the universe has arranged things so that those correlations can never be used to transmit information faster than light. The substrate runs deeper than special relativity, in a sense, but it does not violate the operational predictions of special relativity. It just rearranges the question. It says, there are non-local facts, but they cannot be turned into non-local messages. Whatever is happening down at the substrate is consistent with the world we see at the surface, in spite of being structurally incompatible with the way we describe the surface. This is what physicists mean when they call quantum mechanics compatible with relativity at the level of predictions, but in tension with it at the level of interpretation. The math works. The story does not yet. And there is one more recent result worth mentioning before we move on. In the past few years, physicists have begun to systematically study what they call genuinely multipartite entanglement. Entanglement among 3, 4, 5, or more particles in patterns that cannot be reduced to pairs. A breakthrough in 2026 demonstrated rapid detection of so-called W states, a kind of 3-particle entanglement that has the unusual property of remaining partially intact even if you lose one of the particles. This sounds technical, but the implication is broader. Entanglement is not one phenomenon. It is a family of phenomena, each with its own topology, its own resilience, its own behavior under loss. The realm contains structures that are made out of correlations, the way solid objects are made out of atoms. We are only beginning to map the geography of those structures. And the next question we have to ask, naturally, is this. If measurement seems to play such a special role, if the act of looking fixes what was indefinite, then what counts as measurement? Who counts as an observer? And when, exactly, does the wave function decide what it has been the whole time? That is where we go next. The answer is more disturbing than the questions is less than break time equals 1s is greater than. We have arrived at the part of quantum mechanics where every interpretation crashes into the same wall and tries, with varying degrees of grace, to climb over it. The wall is called the measurement problem, and it goes like this. The Schrödinger equation, the central equation of quantum mechanics, is smooth, continuous, and fully deterministic. Given the wave function at one moment, you can calculate the wave function at any later moment with as much precision as you like. Nothing in the equation says anything about collapse, about choosing one outcome over another, about wave functions narrowing into single answers. The equation just propagates the wave function forward in time, indefinitely, like a wave crossing a pond. But every time we measure a quantum system, we get a single answer. We do not get a superposition of pointer readings. We get one. The detector clicks once. The dial settles on a value. The cat is found alive or dead, not both. The mathematical formalism, which never narrows the wave function on its own, has to be supplemented with a rule that says, when you measure, the wave function collapses to one of its possible outcomes, with probabilities given by the squared magnitude of the wave function at that outcome. This collapse rule, called the Born rule after Max Born who proposed it, is the second pillar of standard quantum mechanics. The Schrödinger equation handles everything between measurements. The Born rule handles measurements themselves. The trouble is that the Schrödinger equation and the Born rule are inconsistent. The Schrödinger equation never collapses anything. The Born rule says collapses happen. Either the equation does not apply to measurements, and you have to say why, or measurements are no different from any other interaction, and you have to explain why we never see superpositions of pointer readings. Neither answer comes easy. This is the measurement problem, and it has not been solved. It has only been moved around. Let me give you the rival accounts, briefly, so you can see why no one is happy. The Copenhagen interpretation, the original story put forward by Niels Bohr and Werner Heisenberg in the late 1920s, treats the line between quantum and classical as primitive. There is a classical world, with definite values and pointer readings. There is a quantum world with wave functions and superpositions. Measurement is whatever happens when the two meet. Don't ask what the cut is made of. Don't ask why nature draws it where it does. Just calculate. The Copenhagen view is operationally successful and philosophically silent. It works in the laboratory and dissolves under careful inspection. The many worlds interpretation, which Hugh Everett wrote down in his Princeton PhD thesis in 1957, takes a different approach. Many worlds says, the Schrödinger equation is all there is no collapse. When you measure a particle in a superposition, you yourself become part of the superposition. Your laboratory becomes part of it. The rest of the universe becomes entangled with you. The branches of the wave function that contain you who saw outcome A cannot, after decoherence, interact with the branches that contain you who saw outcome B. You only experience one branch. But all of them happen, in some sense, because nothing ever collapsed. We will come back to many worlds in detail in a few parts. For now, just note, it solves the measurement problem by saying there is no measurement problem. The wave function never collapses. You just stop being able to see most of it. The pilot wave interpretation, originally proposed by Louis de Broglie and revived by David Bohm in 1952, takes yet another approach. Pilot wave says, the wave function is real, and so are the particles. The particles always have definite positions, and they are guided by the wave function, the way driftwood is guided by ocean currents. The collapse we see in experiments is just our ignorance of the precise initial conditions. The theory is fully deterministic. The price is that it is wildly non-local. The guiding wave is sensitive to conditions everywhere in the universe simultaneously, in a way that cannot be reduced to local interactions. Einstein would have hated this even more than he hated spooky action. Cubism, a more recent contender developed by Christopher Fuchs and Rudiger Schack in the early 2000s, takes the opposite tack. Cubism says, the wave function is not a description of the world at all. It is a description of an agent's beliefs about the world. Quantum mechanics is a tool that agents use to update their expectations based on their experiences. There is no fact of the matter about whether the wave function is real, because the wave function was never a property of the world. It was always a property of the agent. Objective collapse theories GRW, Penrose's gravitational collapse, take a different route. They modify the Schrödinger equation. They add a term that causes the wave function to spontaneously collapse randomly, with a rate so slow that single particles essentially never collapse on their own, but macroscopic objects collapse so often that we never see them in superposition. The Penrose variant ties the collapse rate to gravitational self-energy. Each of these proposals is, in principle, testable. The experiments are now beginning to push into the relevant sensitivity range. Relational quantum mechanics, the brainchild of Carlo Rovelli, takes the most subversive position. There is no observer-independent fact about the state of a system. States are always relative. Two different observers can have, simultaneously, two different and equally correct accounts of what is going on, and there is no neutral perspective from which to ask which one is right. You will notice these answers do not converge, they diverge. The 2025 Nature survey I mentioned at the start showed 45% of physicists believe there is a real boundary between the quantum and classical worlds, and 45% believe there is no such boundary. After 100 years of looking at the problem, the field is split down the middle on the most fundamental question the theory raises. Now let me show you the kind of experiment that brings the measurement problem into the open and forces you to confront it. Consider delayed choice. John Wheeler proposed the thought experiment in 1978. The setup is essentially the double slit, but with a twist. You send single photons through the slits one at a time. After the photon has passed the slits, but before it reaches the detector, You decide whether to set up the detection equipment to record an interference pattern or to record which slit the photon went through. You can make that decision late enough that, by any classical accounting, the photon has already chosen which way to go. The experimental result, when it was finally carried out for real, was clean. The photon's behavior conforms to your choice. If you set up to record interference, you see interference, as if the photon had taken both paths. If you set up to record which path, you see no interference, as if the photon had picked one. The decision you make in the present rewrites the apparent past of the photon. This is not time travel. No information has moved backward in time. What it suggests, however, is that the past is not as closed as we assume. The ledger of what happened, at the quantum level, is not finalized until the present asks the right question. Whether you describe this as the past being indeterminate, or the wave function only collapsing at the moment of detection, or there being no fact of the matter about which path was taken until the experiment is complete, the conclusion is the same. The story of what just happened, down at the substrate, is not written until somebody asks for it. The quantum eraser experiment, a sharper version, makes the point harder still. You encode which path information on a second, entangled photon, then you erase that information after the first photon has hit the screen. When the information is preserved, no interference pattern appears. When you erase it, the interference pattern reappears in the subset of detections that correspond to the erased photons. The interference is not a property of the photons. It is a property of the entire history of the experiment, including events that took place after the photons landed. Now lean in to the most uncomfortable thought experiment ever published, which is called Wigner's Friend. Eugene Wigner wrote it down in 1961. The setup is simple. Wigner's friend is inside a sealed laboratory. The friend prepares a quantum system, puts it through a measurement, and records the result. From the friend's perspective, the measurement happened, the wave function collapsed, the result is fixed, whatever it was. But from Wigner's perspective, outside the laboratory, the entire laboratory friend, apparatus, result, everything is one big quantum system that has not yet been measured. From Wigner's point of view, the friend is in a superposition of having seen outcome A and having seen outcome B. The result has not been fixed yet. The wave function has not collapsed. Whose account is correct? Both. Neither. Each is correct from its own frame. And in 2018, two physicists named Daniela Frauschiger and Renato Renner published a formal version of the experiment in which they showed that, if you push the logic carefully, different observers can come to flatly contradictory conclusions about what happened, and all of them can be internally consistent. The theorem implies that quantum mechanics, taken at face value, cannot be a description of a single shared world. This is what I want you to walk away from this part with. The substrate does not have one timeline. It has overlapping accounts that, on close inspection, do not always agree. The tidy single-world history we live in is the part of the pattern stable enough to be shared across observers. Underneath, the rules permit the kind of contradictions Frauschiger and Renner formalized. Most of the time, decoherence cleans them up so quickly that we never see them, but the formalism does not promise they have to be cleaned up. It only promises that we, with our blunt instruments and noisy environments, will usually fail to see them. We have walked through 3 parts of strange. A thing can be many things. 2 things can be one fact across any distance. The act of looking is what fixes what was indefinite, and the looking can happen after the looking at. Each rule is its own crack in the picture. But there is one more place we have to go before we can talk about what the picture looks like once you stop trying to defend it. We have to look at what is in between the parts, what is in the silence between the atoms, what we call empty space, because, as you probably suspected by now, empty space is not empty either, is less than break time equals 1s, is greater than. Up to this point, we have been walking through the rules of the realm, what particles can do, how they are correlated, how measurement fixes them. We have been talking, in effect, about the actors in the play. Tonight, I want to look at the stage they perform on, the background, the thing we casually call empty space. Because, in keeping with the spirit of this video, empty space turns out not to be empty, and the picture of what is really there is, in some ways, the most unsettling thing we will see together. Let me start by telling you what physicists actually mean by the quantum vacuum. The quantum vacuum is the lowest energy state of all the fields that fill the universe. Modern physics describes matter and forces as ripples in fields: the electron field, the photon field, the quark fields, the gluon field, and so on, all overlapping, all everywhere. A particle is just a localized excitation of one of these fields. Take away the excitation, and you are left with the field at its minimum. That minimum is the vacuum. And here is the trick. The minimum is not zero. The Heisenberg uncertainty principle, which we met when we were talking about the position and momentum of particles, applies equally well to fields. A field cannot sit perfectly still with perfectly definite value. The math forbids it. So even at absolute zero, with no particles around, no light, no heat, the fields continue to fluctuate around their average values. Energy continuously appears and disappears at every point in space, at every moment, in a kind of restless, low-level shimmer. This is the quantum vacuum, not nothing. The minimum of something that cannot be quieted. In 1948, a Dutch physicist named Hendrik Casimir wrote down a prediction that brought the quantum vacuum into the laboratory. He pointed out that if you place two parallel metal plates very close together in a perfect vacuum, the fluctuations of the electromagnetic field between the plates would be restricted to wavelengths that fit between them, while the fluctuations outside the plates could take on any wavelength. The result would be a tiny imbalance of pressure pushing the plates together. The force was small, but, by Casimir's calculation, real and measurable in principle. Stephen Lamoureux, working at Los Alamos, finally measured it in 1997, after improvements in instrument precision made the experiment possible. The Casimir force was there, exactly as predicted. Two metal plates, in a region drained of all matter and light, were pushed toward each other by the difference in vacuum fluctuations between them and outside them. The vacuum had pressure. The vacuum had energy. The vacuum did things. The Casimir effect is now routinely measured in laboratories all over the world. It is no longer a curiosity. It is an engineering constraint. When you build micro-electromechanical systems with parts close enough to feel the Casimir force, you have to account for it, because otherwise your tiny moving parts stick together. The quantum vacuum is, by now, a problem for chip designers. The vacuum also contains what physicists call virtual particles. These are short-lived excitations of the fields, popping in and out of existence so briefly that they cannot be directly detected. They are not metaphor. They are required by the math, and their indirect effects are calculable to extraordinary precision. The anomalous magnetic moment of the electron, the small correction to the electron's interaction with magnetic fields, beyond what the basic theory predicts, is dominated by the contribution of virtual photons and virtual electron-positron pairs flickering around the electron at all times. The calculated value agrees with the measured value to 12 decimal places. We are measuring, with that precision, the influence of particles that do not, in any classical sense, exist. This brings us back to the central thread we have been carrying through this conversation. The realm, when you look at it carefully, denies you the comfortable foundation of a quiet, empty background. The background is not quiet. The background is the most active region of the universe. Every cubic centimetre of empty space contains fluctuating fields with a calculable energy density, and that energy density does measurable work on the matter around it. The substrate is restless, layered, and busy, even where we cannot see it. Now I want to flag, briefly, the largest unresolved tension between quantum mechanics and astronomy. It is called the cosmological constant problem, and it concerns the energy of the vacuum. Quantum field theory predicts an energy density for empty space that is enormous, wildly enormous, depending on how you cut off the calculation, somewhere between 50 and 120 orders of magnitude larger than the value astronomers actually measure when they look at the rate of the universe's expansion. That mismatch, a factor of 10 to the 120th, in some calculations, is the single largest disagreement between theoretical prediction and astronomical observation in the history of physics. Nobody knows why the vacuum energy we calculate is so much larger than the vacuum energy we measure. There are several proposed solutions, none of them universally accepted. Some involve unknown cancellations among different field contributions. Some involve modifications to gravity. Some invoke the anthropic principle and an enormous space of possible universes in which only the ones with small vacuum energy could contain observers. None of them is satisfying. The problem just sits there, on the desk of fundamental physics, glaring at anyone who walks by. The implication for our central thread is this: the realm not only refuses to behave like the everyday world, the realm also, when you ask it what the energy of empty space is, gives you an answer that disagrees with itself by the largest margin in the history of science. The substrate is not even self-consistent in a way we can see clearly. Either our theory of small things is wrong about the vacuum, or our theory of large things is wrong about gravity, or both, or some combination we have not yet imagined. The disagreement is so enormous that whichever direction the resolution comes from, it is going to be major. I want to mention something here, quickly, because it lives in the cultural margins around vacuum energy discussion, and ignoring it feels dishonest. Over the past few years, a handful of patents have been filed by US Navy contractors, attributed to an inventor named Salvatore Pais, describing devices that, on paper, claim to manipulate the quantum vacuum to generate thrust, anti-gravity, or room temperature superconductivity. None of these claims has a verified experimental demonstration. The patents read, to most physicists, as speculation dressed in technical language. They are sometimes called the Pais effect. They circulate in the same online ecosystems as discussion of unidentified aerial phenomena. I am not telling you this because I think they are likely correct. I am telling you because the cultural noise around vacuum energy manipulation is real, and pretending it does not exist would leave a gap in our conversation. The serious science here is the cosmological constant problem. The fringe science here is the patents. They are not the same thing, and you should know which is which. Coming back to the thread, we started this video with the claim that the world we experience is a stable illusion laid on top of a substrate whose rules deny what we take for granted. The vacuum is part of that substrate. The vacuum, viewed at the right level of magnification, is not the absence of stuff. It is the most populated, most active, most uncertain part of the realm. It is a sea that fluctuates, exerts pressure, produces measurable forces, and refuses to give a self-consistent account of its own energy. The realm denies us a stable foundation as completely as it denies us stable particles. There is no quiet floor beneath the strange. There is more strange, which raises a small question that turns out to have an enormous answer. If the substrate is this strange, and if its rules permit things our intuitions forbid, then how do those things actually show themselves in nature? What does the realm do for a living when nobody is watching? That is where we go next. Is less than break time equals 1s, is greater than there is a thing the quantum realm does every day, billions of times a second, inside every star in the night sky, that should not be possible in the world we think we live in. The realm sends particles through solid walls. The phenomenon is called quantum tunneling, and I want to walk you through it carefully, because once you see it, you cannot unsee what it implies about the substrate. Imagine a marble in a bowl. The marble cannot get out of the bowl unless you push it hard enough to climb the rim. The rim is an energy barrier. If the marble's energy is below the rim, the marble stays in the bowl. That is classical physics, and it is the physics you live by. Now imagine the marble is an electron, the bowl is the potential field of a nucleus, and the rim is the energy barrier the electron would have to climb to escape. By the rules you and I live by, the electron stays put. By the rules of the realm, the electron has a small but non-zero probability of simply being found on the other side of the rim without having ever climbed it. It does not punch through. It does not break the wall. It simply turns out to be over there, with no story you can tell about the trip. This is not a metaphor. The wave function of the electron has non-zero amplitude on both sides of the barrier. Most of the amplitude is inside the bowl, where it ought to be. A small amount leaks through to the outside. When you measure, you usually find the electron inside the bowl. Sometimes you find it outside. The percentage depends on the height and shape of the barrier, and the math predicts it precisely. Quantum tunneling is the reason the sun shines. 2 protons inside the core of a star cannot, by classical physics, get close enough to fuse into a single nucleus. Their electric charges repel each other ferociously, and the temperature of the solar core, while ridiculous by human standards, is not actually high enough to push them past the barrier. They cannot climb it. But they can tunnel through. A small fraction of the time, 2 protons drift close together, and one tunnels through the barrier, and the fusion happens, and a tiny burst of energy is released. Multiply that small fraction by the number of protons in the solar core, and you get the 400 trillion watts of power our sun radiates every second. Every photon of sunlight that has ever reached your face started with a particle doing something it was not supposed to be able to do. The realm is what powers the stars. Tunneling also powers your phone. Modern transistors rely on it in subtle ways, both helpful and harmful. The scanning tunneling microscope, invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM Zurich, lets us see individual atoms by bringing a sharp metal tip extremely close to a surface and measuring the current of electrons that tunnel across the gap. The 2 inventors received the Nobel Prize for it 5 years later. Tunneling, in their hands, became a microscope. We see atoms, today, because the realm lets electrons pass through walls. There has been a long, technical debate among physicists about how long the tunneling event takes. The simple man answer was that tunneling is instantaneous. The particle is on one side, then on the other, with no time in between. The Wigner model said no. There is a real, finite traversal time, and it depends on the shape of the barrier. The debate ran for decades. In 2024 and 2025, physicists at the Max Planck Institute for Nuclear Physics in Heidelberg used attosecond precision streaking techniques to actually clock the tunneling event for electrons being ionized from atoms by strong laser pulses. The result is in. Tunneling takes a real, measurable, finite amount of time on the order of tens to hundreds of attoseconds, depending on the barrier. It is not instantaneous. It is also not classical motion. It is its own peculiar process, with its own characteristic clock. Let me also mention 2 close cousins of tunneling that are, in their own way, equally disturbing. The quantum Zeno effect, named after the Greek paradox about the arrow that cannot reach its target because it must always cover half the remaining distance, says that you can prevent a quantum system from evolving by measuring it often enough. Watch the watched pot, in the realm, and it really does not boil. Every measurement collapses the system back to its initial state. Pump enough measurements through, fast enough, and the system is frozen in place. This has been observed in cold atoms, in trapped ions, in superconducting circuits. It is the closest thing to magic that has been replicated in laboratories. Its less famous twin, the anti-Zeno effect, sometimes occurs when you measure at the right speed in the wrong way. In that case, the watching speeds up the evolution. The very same principle of measurement-induced collapse, applied in a slightly different setting, accelerates rather than decelerates the dynamics. Even the rule for what watching does has exceptions, and then there is contextuality. In 1967, two mathematicians named Simon Cochin and Ernst Specker proved a theorem that I find, frankly, the most unsettling result in the entire foundations of quantum mechanics, more so even than Bell's theorem. The Cochin-Specker theorem says that you cannot, even in principle, assign predefined values to all the measurable properties of a quantum system in a way that is consistent with quantum predictions. The properties cannot all be there, waiting to be discovered, in any logically coherent way. The result you get from a measurement depends on what other measurements you happen to choose to make alongside it. Read that again. The result depends on the context of measurement, not on hidden variables, not on the system having properties we cannot see. There is no consistent assignment of values that quantum mechanics permits before measurement. The properties are not, in any meaningful sense, there before you ask. They are co-created by the asking. This is what physicists mean by contextuality, and it is the strongest argument against the naive picture of nature as a collection of objects with their own properties. Nature, at the quantum level, does not admit such a picture. It does not contradict it. Exactly. It just refuses to be made of it. The realm is not a warehouse of items waiting to be inspected. The realm is a pattern that responds to the questions you put to it, with answers that depend partly on the answer and partly on the question. Let me stop and pull this back to the central thread we have been carrying. We started this video with the claim that the world you experience is a stable illusion laid on top of a substrate whose actual rules deny location, identity, history, and possibly even a single shared reality. With each part, we have gathered another piece of evidence for that claim. The realm permits tunneling denial of barriers. It permits the Zeno effect denial that measurement is a passive look. It permits contextuality denial that properties exist independent of inquiry. None of these is a peripheral curiosity. Each is a structural feature of the substrate, woven into the math, confirmed by experiment. There is also a stranger cousin of tunneling that I want to flag before we leave this part, because it shows up everywhere once you know to look for it. It is called macroscopic quantum tunneling, and it refers to cases where, instead of a single particle tunneling through a barrier, an entire collective state of many particles tunnels through together. The flux states inside superconducting circuits do this. So do certain magnetic domains in nanostructured materials. The collective tunneling rate is exponentially smaller than the single particle rate, but it is not zero. Things made of trillions of particles can, on rare occasions, do collectively what a single particle can do, pass through a barrier they could not classically cross. This means that, strictly speaking, the rules of the realm apply not just to the things inside atoms, but to the atoms themselves, and to the molecules they form, and to the materials those molecules build. The walls between scales are leakier than we like to admit. Now, let me push contextuality a little further, because I think it is the most underrated result in the foundations of physics, and most popular treatments do not give it the attention it deserves. The Cochin-Specker theorem rules out a particular kind of realism, the kind in which all the measurable properties of a quantum object have definite values before measurement. But it does not just rule out hidden variables. It rules out the broader picture of nature as a collection of objects with their own private property lists. If contextuality is correct, then the question, what is the spin of this electron about the vertical axis, does not have an answer in the absence of a measurement context, and the answer it gets when measured depends on what other measurements the experimenter chooses to make alongside it. The implication is that the realm does not have items in it the way a warehouse has items. The realm has a kind of relational structure, in which what counts as a property emerges only when a question is asked. The questioning shapes the response. This is not consciousness causing collapse, please do not hear that. It is a much more subtle claim. The properties of quantum objects are not independent of the measurement context, in the same way that the value of a polynomial is not independent of where you evaluate it. You do not get to pull the polynomial apart from its evaluation. They are bound together. This is what the realm seems to be like, all the way down. Not a collection of items waiting for someone to look at them, but a pattern that responds to interrogation with answers that depend partly on the interrogation. Whatever you do to it, you are part of it. Whatever you see, your seeing changed. But there is one more piece of strangeness we have to walk through before we can talk about what it all implies. The wave function, the central mathematical object of the entire theory, the thing we have been using and naming throughout, has a feature so unsettling that, even today, most physicists prefer not to think about it directly. The wave function does not live in our universe. That is where we go next. And it is where the picture of reality we have been holding starts, in earnest, to come apart, is less than break time equals 1s, is greater than. We need to look directly at something I have been hinting at for several parts. The wave function is the central mathematical object of quantum mechanics. It is what we calculate. It is what carries the predictions. Whatever the realm is doing, the wave function is our best description of it. And the space the wave function lives in is not the space you and I live in. Let me explain that as plainly as I can. For a single particle moving in three-dimensional space, the wave function is a function from three coordinates to a complex number. You give it a location, it gives you back an amplitude. The squared magnitude of the amplitude is the probability density of finding the particle at that location. This is fine. This fits in your head. For two particles, the wave function is a function from 6 coordinates to a complex number. 3 for the position of the first particle, 3 for the position of the second. Crucially, you cannot, in general, factor this wave function into a product of two single particle wave functions. That is what entanglement means. The wave function of the entangled pair is not a wave for particle A times a wave for particle B. It is a single object that takes 6 coordinates and returns one amplitude, and the value at any given 6-coordinate point depends on both particles at once. For 3 particles, you need 9 coordinates. For 4, 12. For n particles, 3n coordinates. The space that holds the wave function is called configuration space, and it has 3 dimensions per particle. A glass of water contains roughly 10 to the 25th molecules. Each molecule has many atoms, but let us be generous and just count molecules. The wave function of the water in the glass, if you took quantum mechanics at face value, would be a function of 3 times 10 to the 25th coordinates. That is more dimensions than there are atoms in the observable universe. This is not exaggeration. It is what the math requires. If you try to project the wave function down into 3-dimensional space, your space, my space, the space we share, you lose the interference effects we measure in laboratories. You cannot describe entanglement, the most well-verified feature of quantum mechanics, in 3 dimensions. You need the higher dimensional configuration space, with one set of coordinates per particle and the wave function defined across all of them. This is what physicists mean when they say the wave function is in Hilbert space or in configuration space. They are not being poetic. They are pointing at the literal mathematical object that does the heavy lifting in their predictions. And that object does not fit inside the universe you see. Now you have two choices, and they are both upsetting. Choice 1. The wave function is not really real. It is a calculational fiction, a bookkeeping device, a clever piece of mathematics that, for reasons we do not understand, makes flawless predictions about the world, but does not itself correspond to anything physically existing. On this view, what is real is just the outcomes, the clicks of detectors, the readings of pointers, the dots on a screen. The wave function in between is, as Niels Bohr essentially said, none of your business. Don't ask what the world is doing between measurements. Ask only what the world will do when you measure it. The continuous existence of objects between observations is a story we tell ourselves out of cognitive habit. This is, I should say, the dominant practical position among working physicists, not because anyone has positive arguments for it, but because it lets them get on with their day. The framework calculates correctly. The interpretation is set aside. The textbooks call this the shut up and calculate school, and it is the most popular interpretation of quantum mechanics, even though it is, strictly, not an interpretation at all. It is the refusal to interpret. The price of this choice is that you have to accept that physics, the most predictive enterprise in human history, has at its center a mathematical object that is not real and does not represent anything in the world. You are using a fiction to predict the future with perfect accuracy, and you are not allowed to ask why the fiction works. This is, I think, harder to live with than people admit. Choice 2. The wave function is real. Then the wave function is not in our three-dimensional space. It is in a much higher dimensional space. And the three-dimensional world we experience is, in some sense, a projection or a shadow of a higher dimensional reality. This is the position taken seriously by, among others, the philosopher David Albert at Columbia. Albert's argument is that if you want quantum mechanics to be a description of a real world, if you want the wave function to refer to something, then the world has to be the wave function. The three-dimensional appearance is a derived feature. The underlying reality is the wave function moving through configuration space, and we ride on top of it as a kind of effective three-dimensional cross-section. You can choose to believe this. Many serious philosophers and a small minority of physicists do. The price is that you have to give up the idea that the world you see is the world that exists. The world you see becomes a layer. The substrate is bigger than the room. Either way, you are giving something up. There is no third door that lets you keep both the three-dimensional world as fundamental and the wave function as describing it. The math forbids that combination. Bell's theorem, which we met in the entanglement part, is another way to see the same fork. Bell showed that you cannot have all of the following simultaneously: particles with definite properties before measurement, signals respecting the speed of light, and the experimenter's freedom to choose what to measure. Quantum mechanics requires you to give up at least one. Most physicists give up the first locality of properties. A few give up the second, strict relativistic causality at the level of correlations. A few, the superdeterminists, give up the third and accept that the universe was set up at the Big Bang in such a way that every choice we appear to make was, in fact, already correlated with the result we will find. Each of these is its own form of giving up the picture of a world made of separate objects with their own private histories. Each is its own form of accepting that the substrate is bigger, deeper, or stranger than the foreground. The math is consistent. It just is not consistent with everything we wanted to believe at once. I want to give you one more way to feel the dimensional problem, because most introductions treat it as a technicality, and it is not a technicality. Imagine you are watching a movie projected on a flat screen. The screen is two-dimensional. Everything you see is a flat image. But the events the movie depicts, characters moving through rooms, cars driving down streets, planets turning in space, happen in 3 dimensions. The screen is a projection. The action lives in a higher dimensional space, and the screen catches a flattened image of it. When something on the screen looks impossible, when shadows seem to fall in directions they should not, when objects seem to grow or shrink for no reason, the screen does not tell you why. The reason lives in the three-dimensional original, which the screen cannot show. The configuration space problem is the same shape of issue, scaled up. The wave function lives in a space whose dimensionality grows with the number of particles in the system. Our three-dimensional world is, in effect, a projection of that higher dimensional object onto the tiny subspace we can perceive. The interference effects we measure are the equivalent of impossible shadows on the screen. They hint at the existence of a higher dimensional reality whose structure determines what we see. We cannot see the higher dimensional space directly. We see only its three-dimensional projection, but the projection carries with it fingerprints of the larger structure, and those fingerprints are the strange quantum effects that nothing local can explain. If this is the right picture, then the universe you experience is, quite literally, the surface of something larger. The realm is not a hidden room beneath the world. The realm is the original, of which the world is a flattened copy. And the strange effects we measure in laboratories are not anomalies. They are the parts of the original that refuse to flatten cleanly. I want to be careful here, because we are now at the edge of speculation. Not every physicist accepts the wave function realist position. Many would say the configuration space talk is a useful calculational fiction and that the world really is three-dimensional, period. They would say the shadow picture is overinterpretation. I am not insisting otherwise. I am pointing out that this is one of the live possibilities the math forces on the table. It is not the only possibility, but it is on the table, and it has been on the table for the entire century of quantum mechanics, and nobody has yet managed to remove it. And here is where the central thread of our video sharpens to its edge. We have been arguing, all along, that the world we experience is a stable illusion riding on top of a substrate that denies our intuitions. The configuration space problem is the strongest single piece of evidence for that claim. Even at the level of the mathematical formalism, before we get to interpretation, the framework already tells us that the natural home of physics is not our three-dimensional space, it is somewhere else. We are, in some technical sense, living in a low-dimensional shadow of an object that we cannot fully see. If you take that seriously, and the math gives you very little choice, then the next question is one of the most upsetting in all of physics. If the wave function is real, and if it never collapses, then what happens to the parts that, at any given measurement, did not become what you saw? What happens to the branches that contain the other outcomes? There is an answer. It is well known. It is also the answer most people, when they hear it, do not want to be true. That is where we go next. Hugh Everett, in his Princeton PhD thesis in 1957, wrote down what he thought was a small clarification to the mathematics of measurement. What he actually wrote down was a theory of personal identity in which there is no single you. Is less than break time equals 1s is greater than. In 1957, a young graduate student at Princeton named Hugh Everett III turned in a PhD thesis with a title that, on the surface, looked modest, On the Foundations of Quantum Mechanics. Inside, the thesis was a proposal that, taken seriously, rewrites the picture of reality we have been walking through. The proposal is now called the many worlds interpretation, and it goes like this. The Schrödinger equation is all there is. There is no collapse. When you measure a quantum particle, you do not select one outcome from a set of possibilities while the others vanish. Instead, you, your laboratory, the apparatus, the lab assistant in the hallway, the air in the room, and everything that becomes entangled with the measurement enter a single grand superposition together. There is a part of the wave function in which you saw outcome A and went home for dinner thinking about it. There is a part of the wave function in which you saw outcome B and went home thinking about something else. Both parts exist. Both parts evolve under the Schrödinger equation forever. The parts cannot, after decoherence, interact with one another because the environment has been entangled with the measurement and the relative phases between the branches have been scrambled beyond any practical possibility of recovery. From inside each branch, it looks as if the wave function collapsed and the world picked one. From outside, if there were an outside, which there isn't, it would look like a single, ever-branching, deterministic universal wave function in which every possible outcome of every quantum event happens somewhere, that is, many worlds. You can see why Everett thought this was a clarification rather than a revolution. The Schrödinger equation already says the wave function does not collapse. Many worlds simply takes that fact at face value and refuses to add a collapse step. The interpretation is, in a real sense, the minimal interpretation, the one you arrive at if you take the math seriously and do not add anything to it. Everett did not want to invent multiple universes. He wanted to delete a step from the textbook that, in his view, did not belong. His advisor John Wheeler liked the idea well enough to send Everett to Copenhagen to meet Niels Bohr. The meeting did not go well. Bohr, the dean of the Standard View, dismissed the proposal. Everett left academic physics shortly afterwards and spent the rest of his career working on operations, research, and nuclear strategy at the Pentagon. The interpretation he left behind sat largely ignored for 2 decades until decoherence theory developed in the 1970s and gave it a much firmer footing. What changed in the 70s and beyond was this. Wojciech Zurek and others showed that the apparent collapse of the wave function in measurement can be derived as a consequence of decoherence, the rapid entanglement of the measured system with its environment. Once decoherence has done its work, the different branches of the wave function become, for all practical purposes, unable to interact. They do not vanish, they simply become unreachable from one another. The classical world we experience is what one branch looks like from inside. This made many worlds, suddenly, much more defensible. The strangest feature of the proposal, that all those branches keep existing, turned out to be a clean consequence of the math, once you stopped imposing collapse by hand. The proposal stopped looking like a wild add-on and started looking like the most economical reading of the Schrödinger equation. The 2025 Nature survey showed that about 15% of physicists now prefer many worlds as their working interpretation. That is up from essentially 0 in the 1950s. The number is rising slowly, partly because the alternatives all have their own problems. Copenhagen has the measurement problem, Pilot Wave has wild non-locality, Cubism abandons the project of describing the world, and partly because many worlds, in its modern dressing, just keeps not breaking under examination. Let me now describe what many worlds implies for you, since this is the part that turns physics into a strange kind of personal news. If many worlds is correct, there is no single timeline of your life. There is a tree. Every quantum event that could have gone differently has gone differently in some branch of the wave function. Every choice you have ever made, insofar as the choice had any quantum origin in your neurons or your environment, has been made differently in another branch. Every dice roll, every electron spin, every photon you almost saw but missed because it scattered the other way, every breakthrough you almost had, every accident you barely avoided, every conversation that turned out one way and almost turned out another. All the others happened too. The you that is hearing this is one leaf on a tree that is unimaginably large. Now, here is where I want to be careful, because the rest of the implications of many worlds get dark very quickly if you do not handle them with care. There is a thought experiment in the literature called quantum suicide, written about most prominently by Max Tegmark. The thought experiment exists in the technical literature as a way of probing what many worlds means. It is not a recommendation. It is not a how-to. It is a logical structure designed to highlight a problem with the interpretation. I mention it here only because it is part of the public conversation around the theory, and to leave it out would be incomplete. Tegmark himself argued the thought experiment did not actually work, that personal identity in many worlds is more subtle than the simple version assumes. Move on. There is also, in popular discourse, the so-called Mandela effect, the internet phenomenon in which large numbers of people misremember the same historical fact in the same way, sometimes attributed by online speculators to branch jumping between parallel universes. The serious answer is that this is what human memory does. Memory is reconstructive. Many people, given the same partial cues, produce the same plausible-sounding wrong answer. The Mandela effect is a fact about cognition, not a fact about many worlds. The interesting question is why the speculation appeals. The answer, I think, is that the math, taken seriously, does say something close to the speculation's flavour. We are a leaf. There are other leaves. The mind, when it confronts that thought, reaches for the nearest folk explanation it can find. There are other interpretations of quantum mechanics that try to avoid the branching tree of many worlds. Pilot wave restores determinism by saying particles always have positions, guided by a real wave. The price is wild non-locality and a kind of preferred frame of reference that sits uneasy with special relativity. Cubism says the wave function is a description of an agent's beliefs and not a description of the world. The price is that quantum mechanics stops being a theory of the physical world at all, and the universe contains nothing but agents and their experiences. Objective collapse theories like GRW and the Penrose proposal modify the Schrödinger equation to add a spontaneous collapse mechanism. The price is that you have to write down a precise rate of collapse, and the rates that fit the data also predict effects that future experiments can rule in or rule out. Relational quantum mechanics, Ravelli's proposal, says there is no observer-independent fact about what is real. The price is that physics stops describing a world and starts describing a network of relations between observers. I am not advocating any one of these. The point is that all of the options the math allows are disturbing in their own way. There is no interpretation of quantum mechanics that gives you back the world you thought you lived in before you started looking. The substrate makes you choose between giving up a single timeline, a single shared reality, a single location for objects, or a single description that all observers agree on. Pick whichever loss you can bear. And here is the connection back to our central thread. Whichever interpretation turns out to be correct, and the 2025 survey makes clear that the field is still genuinely divided, the substrate denies us the comfortable picture of a single shared world with a single shared history that all observers can confirm. The realm is the place where that comfort was never available. We had it on loan from the noise of decoherence. The price of looking closely is realizing the loan is up. There is one more place to go before we land. Up to this point, we have talked about the realm as if it were a thing we look down into from above, as if we were classical observers studying a strange, smaller world. That framing has been a useful simplification, but it is now time to drop it. Because the rules we have been describing do not stop at the boundary of your skin, they run through you. You are not standing at the lip of the realm looking in. You are made of it. That is where we go next. And the news, when it lands, is not external. It is internal. Is less than break time equals 1s. Is greater than... I want to take this part somewhere unusual for a science video. For most of this conversation, we have talked about the quantum realm as if it were down there, somewhere far away, a strange territory we study with expensive instruments. That framing has done useful work for us, but it has also been quietly misleading. The realm is not down there. The realm is how you exist. The same rules we have been walking through are what your blood does. They are what your eyes do when light hits them. They are, possibly, what your nervous system does when it does the thing we cannot otherwise explain, when it produces the experience of being someone. Let me start with the part that is solidly established science, and then walk carefully out toward the edge. The science that is solid is called quantum biology, and it is the study of cases where living systems exploit quantum effects to do their work better than classical chemistry alone would allow. This used to be considered impossible. The traditional argument was that quantum coherence, the maintenance of phase relationships between different parts of a wave function, requires very cold temperatures and very isolated systems. The interior of a living cell is warm and wet and noisy. The wisdom was that decoherence would destroy any quantum behavior in a cell long before it could do anything biologically useful. The wisdom was wrong. Several lines of evidence since the late 90s and especially the 2000s have shown that quantum effects are not just present in living systems, but are actively used by them. Take photosynthesis. The pigment protein complexes in green plants and photosynthetic bacteria do an astonishing thing. They absorb a photon at the surface of a chlorophyll molecule and then transport the energy through a network of pigments to a reaction center where the energy is used to drive chemistry. The transport is extraordinarily efficient. Almost every photon absorbed delivers its energy to the reaction center. In a purely classical picture, the energy would have to take a particular path through the pigment network, and the path is not always the most efficient. In a quantum picture, the energy can be in a superposition of taking all possible paths simultaneously, like the electron in the double slit, with constructive interference picking out the most efficient route. 2007, Greg Engel and his collaborators at Berkeley demonstrated, using two-dimensional electronic spectroscopy, that quantum coherence does in fact persist in the Fenner-Matthews-Olson photosynthetic complex of a photosynthetic bacterium at temperatures up to 80 Kelvin, and there is now substantial evidence for related effects at physiological temperatures in actual plants. The leaf, as a device, exploits quantum interference to harvest sunlight more efficiently than classical chemistry alone would manage. The plant is, in a real sense, a quantum machine. Now, look at European robins. They navigate using the Earth's magnetic field, and they have been observed to do so even when the magnetic field is extremely weak, far too weak for any classical compass mechanism in a biological system to detect. The leading hypothesis, with strong experimental support, is that the robin's eye contains a molecule called cryptochrome, and that when blue light strikes cryptochrome, it produces a short-lived pair of electron radicals, molecules with unpaired electrons whose spin states are quantum correlated. The spin states are sensitive to the local magnetic field. The bird, looking around, sees a faint pattern overlaid on its vision that depends on its orientation in the magnetic field of the Earth. The fact that this mechanism works at all is remarkable, because the radical pair has to maintain spin coherence for hundreds of microseconds inside a warm, noisy biological molecule. Under generic physical assumptions, the coherence should disappear in nanoseconds. Evolution has, apparently, tuned the cryptochrome molecule to protect coherence longer than physics naively allows. The robin sees the planet's magnetic field as a quantum coherent signal in its eye. The migration patterns of half the songbirds on the planet may depend on a sustained quantum coherence in a single protein. There is also evidence, older, more controversial, still being worked out, that enzymes use quantum tunneling. Hydrogen atoms involved in some enzyme-catalyzed reactions appear to tunnel through energy barriers that classical chemistry says should require much higher activation energies. Without this, the rates at which enzymes do their work would be much lower, and biochemistry might not function fast enough to support life as we know it. The realm, in this picture, is not exotic. The realm is what makes you metabolize your dinner. So far, this is all reasonably well established. The leaf catches photons quantum mechanically. The bird navigates by spin coherence. The enzyme tunnels. The realm is, in a real and verified sense, running through the biology of the living world. This brings us closer to the central thread of our conversation than any other piece of evidence we have walked through. The strange rules are not far away. The strange rules are how you function. Now, I want to walk us carefully toward the speculative edge, because there is real science there, real published work, but the consensus is not as solid as it is for photosynthesis or bird navigation. I will flag clearly where the speculation begins. Roger Penrose, the Oxford mathematician and physicist who shared the 2020 Nobel Prize for his work on black holes, has for decades argued that consciousness is, in some way, a quantum phenomenon. In collaboration with the American anesthesiologist Stuart Hameroff, Penrose has developed a model called Orchestrated Objective Reduction OR for short. The proposal is that the cytoskeleton of neurons contains small protein structures called microtubules, and that the microtubules can sustain quantum coherence among electrons inside them. The coherence, on Penrose's theory, lasts long enough for a quantum computation to take place, and conscious experience arises when the coherence is brought to an end by what Penrose calls objective reduction, a spontaneous collapse driven in his model by gravitational self-energy. Most neuroscientists reject the model. The standard objection is the same one that applied to quantum biology before the experiments came in. Biological matter is too warm and wet to sustain coherence long enough to matter. In 2023 and 2024, however, some experimental groups reported finding longer than expected coherence times in microtubule-related systems. Penrose's supporters cite these as evidence that the model deserves more serious attention. Critics call the results inconclusive. The question is open. In December of 2025, a paper appeared proposing that cortical microcolumns in the brain might couple directly to the zero-point field of the quantum vacuum. The proposal is speculative. Most physicists I respect treat it with cautious skepticism. But the fact that the proposal exists at all, in a respectable forum, indicates how unsettled this territory is. Once you accept that the realm does work inside leaves and inside bird eyes, the question of whether it does work inside neurons becomes much harder to dismiss out of hand. I want to be clear here. I am not telling you that consciousness has been shown to be quantum. It has not. The leading theories of consciousness in mainstream neuroscience do not involve quantum effects at all. The Penrose-Hameroff proposal is a minority view, and the cortical microcolumn paper is one paper. What I am telling you is this. The quantum realm, taken seriously, does not stop at the boundary of biology. It runs through living systems in well-verified ways, and the question of how far up it runs into the nervous system is not yet settled. There are serious physicists, including a Nobel laureate, who think the realm does meaningful work inside your head. They might be wrong. They might be right. The fact that the question is not laughable in 2026 is itself the news. And here is where I want to bring this back to the central thread we have been carrying. The substrate is not a thing we visit from outside. It is not down there, far away, behind a barrier. It is the floor we stand on, the air we breathe, the molecules that catch sunlight inside our skin, the enzymes that release the energy of our food, possibly the proteins that run the navigation of birds, possibly the structures that produce, somehow, the experience of being someone. We are not external observers of the realm. We are, in a literal and verifiable sense, made of it. The strange rules we have been walking through are, in some genuine sense, our rules. This is why the title of this video says the realm is disturbing. The disturbance is not that there are weird small things far away from us. The disturbance is that we are not as separate from those weird small things as we wanted to believe. The line we have been drawing between the realm and us is, on close examination, not where we drew it. It is somewhere else, possibly nowhere at all. There is one part left in our conversation. It is the part where we put the picture together and ask what to do with it. We are going to end on a synthesis, not on a horror. The realm is not malevolent. The realm is consistent with itself, mathematically precise, and entirely indifferent to whether you can understand it. What it asks of you, in return for looking at it carefully, is that you give up some of what you thought the world was. We will see, in the final part, what is left when you do. Is less than break time equals 1s, is greater than... Let me walk back through what we have seen, slowly, the way you might walk through a house you grew up in after a long absence. Each room held an assumption you used to live by. Each room, in turn, has had its furniture rearranged. We started with the quiet discovery, 100 years of the most predictive theory in the history of science, and physicists still cannot agree on what the theory is describing. The 2025 Nature Survey told us 45% yes, 45% no on the existence of a real quantum classical boundary, 15% for many worlds. The rest scattered across a half-dozen rival pictures. Underneath the disagreement, the math keeps making correct predictions. The world keeps coming out the way the equations say it will. We just do not know what kind of world that is. Then we walk down through scale, from a strand of hair to the size of an atom, and watch the rules switch over. The atom is overwhelmingly empty space. The electron has no position in the same sense the marble at the center does. Energy comes in steps. Continuous-looking quantities are mosaic underneath. Most of what feels solid is not. The part that is not empty does not behave the way you expect. We met superposition. A thing can be many things at once. The other possibilities are not bookkeeping. They leave fingerprints in the form of interference. The wave function lives in a space that grows with the number of particles it describes, until, for the things we hold in our hands, it lives in more dimensions than there are atoms in the visible universe. Either the wave function is not real, and the most predictive theory in science is built on a fiction, or the wave function is real, and the world you see is a shadow cast from a higher dimensional space. We met entanglement. Two particles, once joined in a single quantum state, share a single fact across any distance, with no story you can tell about how it travels between them. Bell's theorem, aspects experiments, the 2022 Nobel, the question is settled. Local realism is dead. Entanglement is not a special trick. Entanglement is the structural state of matter. The everyday solids around you are knotted at the quantum level all the time, and the only reason the knots are invisible to you is that decoherence washes the visible signatures out before you can see them. We met the measurement problem. The Schrödinger equation never collapses. The Bohm rule says collapses happen. The two cannot both be exactly right. The interpretations multiply. Delayed choice experiments show that the present can rewrite the apparent past. Wigner's friend and Frauchiger-Renner show that, taken at face value, the theory implies different observers can come to logically contradictory conclusions about what happened, all of them correct in their own frame. The substrate does not have one timeline. It has overlapping accounts. We met the vacuum. Empty space is not empty. It fluctuates, exerts pressure, produces measurable forces, and disagrees with itself by the largest margin in scientific history on the energy density it ought to have. The cosmological constant problem sits there, glaring at anyone who walks past, and nobody has a clean solution. The substrate refuses to provide a quiet foundation. The foundation is more strange. We met tunneling and contextuality. Particles pass through walls. The sun shines because of this. Microscopes see atoms because of this. The Cauchy-Specker theorem tells us that properties of quantum objects are not, in a meaningful sense, there before you ask. They are co-created by the asking. There are no items in the warehouse. There is only the pattern responding to your inquiry. We met the configuration space problem head-on. The wave function does not fit in our universe. We must give up either its reality or our world's three-dimensionality as fundamental. There is no third door. We met many worlds. The math, taken at face value, says that every measurement outcome happens in a branching wave function that never collapses. 15% of physicists, and rising, think this is the cleanest reading. The implication for you is that you are not a single thread, but a delta-1 leaf among an unimaginably large tree of leaves, all of which are you, none of which is more real than another. Even if many worlds turns out to be wrong, all the alternatives carry their own kind of upending. Pilot wave's wild non-locality. Cubism's elimination of the world from the theory entirely. Objective collapses, modification of the Schrödinger equation itself. Relational quantum mechanics' denial that there is any observer-independent fact about what happened. There is no painless option. We met quantum biology. The realm runs through the leaf, through the bird's eye, through the enzymes in your body. We are not outside observers of the realm. We are made of it. The boundary we keep wanting to draw between down there and up here gets harder to maintain the more carefully you look. That is what we have walked through. Now I want to bring it to its conclusion. There is an account, due to Wojciech at Los Alamos, of why the classical world we experience emerges from the quantum substrate. The account is called Quantum Darwinism, and it is, I think, the closest thing modern physics has to an explanation of the appearance of solidity. The idea is that some quantum states are stable against decoherence because they get redundantly recorded into the environment. The position of a chair, for example, scatters trillions of photons every second, each of which carries a copy of the information about where the chair is. Many independent observers can read those photons and converge on the same conclusion. The chair is here. The chair is solid. The chair is in one place. The classical world is what survives this Darwinian filtering. The states that get broadcast in many redundant copies are the ones we all see, and the ones that do not get broadcast, the genuine superpositions, remain invisible to us. This is elegant. It also has a quiet implication. The classical world is not the foundation. The classical world is the consensus reading of the broadcast. It is contingent on the structure of the environment that does the broadcasting. There are events at the substrate that never become classical. They simply remain in the realm, unread, doing whatever they do. The clean shared world is what comes out of a particular kind of dirty filtering. It is not the underlying reality. It is a stable summary. Now, at the other end of the scale, there is a problem the substrate is still wrestling with, the black hole information paradox. Stephen Hawking, in 1974, calculated that black holes should emit a faint thermal radiation, now called Hawking radiation, and slowly evaporate. The trouble is that, on a naive reading of Hawking's calculation, the radiation carries away no information about what fell into the hole, so the information seems to vanish. But quantum mechanics demands that information cannot be destroyed. The substrate's deepest principle and the gravitational substrate's deepest principle cannot both be right in the simple forms we have written down. The conflict has occupied physicists for half a century, and a resolution involving non-local entanglement across the black hole horizon, the so-called island formula, has, in the last few years, started to converge on an answer that preserves quantum information. The work is not done. The point is that even at the largest scale, the substrate insists on its rules. The realm shows up everywhere physics looks. In the meantime, we are building infrastructure with these rules. Google's Willow chip, in late 2024, demonstrated quantum error correction that scales logical qubits, whose error rate drops as you add more physical qubits, the breakthrough that the entire field had been chasing for 30 years. IBM, Quantinuum, the Chinese photonic platforms, and a half-dozen academic groups are now racing to build machines that exploit superposition, entanglement, and interference to compute things classical computers cannot. The substrate is being weaponized into machinery. We do not need to understand the realm to use it, we just have to obey it. The quantum computer is the proof of concept. It is what 100 years of taking the realm seriously have built. So bring this back to the title, what is hiding inside the quantum realm? The answer, walked through carefully, is not what most people expect. What is hiding is not a monster. There is no creature down there waiting to be unleashed. There is not a hidden dimension full of things you have not yet been told about. There is not a secret government program suppressing the truth. What is hiding is the slow, accumulating suspicion that the world you think you live in is not the world that actually exists. The world you live in is the projection. The realm is the source. The line we have spent our lives drawing between things out there and ourselves looking at them is, on close inspection, not where we drew it, possibly nowhere at all. The substrate runs through everything, including the observer, including the act of observation, including the words I am saying to you and the meaning you are extracting from them. We are not external to the realm. We never were. The realm has been doing its work inside us this entire time, and the only news, after 100 years of careful study, is that we have noticed. The disturbing part is not the weirdness. The weirdness is well documented. The disturbing part is the consistency. The realm is consistent with itself, predictively flawless, mathematically beautiful, entirely indifferent to whether you can understand it. It does not owe us a clean picture. It does not promise us a stable foundation. It does not guarantee that there is a single shared world for everyone, or that the past is closed, or that you are one person rather than a delta. It just is what it is, and we are its inhabitants, and our intuitions about what the world is were made for a very different scale and a very different kind of problem. The door, once opened, cannot be closed. You can stop watching this video. You can turn off the lights and pull the blanket up to your chin. You can sleep. The realm will keep running underneath. Your atoms will keep being mostly empty space. The electrons in your brain will keep tunneling through small barriers as you dream. The entanglements that have been built up across your body over your lifetime will not unmake themselves. The substrate will keep doing what it has always done. You will simply have learned, tonight, that it is doing it. I do not think this is a horror story. I think it is the slow, patient, unspectacular news that we are stranger than we look. The world is stranger than it looks. The universe, at its smallest scale, is the most carefully balanced, most subtle, most precisely tuned thing science has ever found, and it operates by rules that you and I cannot picture. We will spend the rest of our species' existence trying to understand what those rules mean, and we may never finish. The job will outlive every one of us. But that is what it means to live in a real universe. The universe is not a stage set built for human comprehension. The universe is something much older and much larger and much subtler than that. We are made of it. We are inside it. And, after 100 years of looking very carefully, we have finally begun to notice that the room we live in is not the building, and the building is not the city, and the city is not the country, and we have not yet found the edge of what surrounds us. So here, finally, is what I want to leave you with tonight. The universe at its smallest scale is consistent with itself, mathematically perfect, predictively flawless, and entirely indifferent to whether you can understand it. You are made of something that does not behave the way you behave. You are watching, right now, with eyes whose every cell runs on rules you cannot picture. The realm is not down there. The realm is here. It has always been here. And the only reason it feels strange is that finally, after 100 years, we have started to notice sleep well. The substrate, for what it is worth, will keep running while you do.